In this video, we will look at an application of exponential functions related to half-life. A patient is given 50 milligrams of a drug that has an average half-life of 20 hours. We want to write an exponential model of the form P of t, which equals P sub 0 e to the kt, that represents the amount of the drug in the patient's bloodstream t hours after the medicine is administered. Round the value of k to 5 decimal places. Then our second part is a patient is given a second dose of 50 milligrams in 6 hours. How much of the drug is in the patient's bloodstream after the second dose is administered? So these problems are pretty cool in the sense that if I know an initial amount and I know the half-life, I can come up with an exponential model. Because remember what our formula requires, P of t, which is equal to P sub 0 e to the kt, tells us if we know 3 of the values, we can find the 4th. Given 50 milligrams and a half-life of 20 hours, we actually know 3 of the values, even though 2 are explicitly stated. We know that if we start with 50 milligrams, that in 20 hours, we're going to have 25 milligrams remaining, right? The half-life is the time it takes for half of the substance to remain. So we know a beginning amount of 50, an ending amount of 25, and the time it took for those changes to occur. We're going to substitute 25 for our ending amount. Our initial amount is 50, and we're going to substitute 20 for t. So our equation that we will solve is 25 equals 50 e to the k times 20. To get the variable factor on the side by itself, we're going to divide each side by 50. 25 divided by 50 is 1/2, or 0.5, equals e to the 20k. To solve for k, we're going to take the natural log of each side. So the natural log of 0.5 is equal to the natural log of e to the 20k. We get the natural log of 0.5 is equal to 20k. Then we can divide by 20. So the natural log of 0.5 divided by 20 tells us that k is approximately negative 0.03466. And just to put a check in there, because we're talking about decay, right, half-life, decreasing amounts, we should have a negative value of k. So the model that we need to write is P of t, which equals to our initial amount of 50, so P of t equals 50, times e to the k, which is negative 0.03466 t. To answer part B, we're told that a patient is given a second dose of 50 milligrams in 6 hours. How much of the drug is in the patient's bloodstream after the second dose is administered? Well, we have to think about what remains of the first dose and then add the second dose to it to figure out how much is in the patient's bloodstream. So we first need to figure out how much is left in the patient's bloodstream after 6 hours, then we'll add that to the amount of the second dose. So in 6 hours, we're going to find that value by determining P of 6. P of 6 is 50 times e to the negative 0.03466 times 6. And substituting that expression on the calculator gives us that P of 6 is approximately 40.6 milligrams. So if we had 40.6 remaining from just a natural decay, plus the 50 that was given, the total in the patient's bloodstream is then the 50 milligrams from that second dose, plus what was remaining, the 40.6 milligrams, to get 90.6 milligrams. There are certain drugs where this would be toxic, right? So these are things that doctors and nurses need to take into consideration, the half-life, to determine when is the appropriate time to give another dose of the medication.